Now we can move to the next speaker. It's my great pleasure to present Annarita Giani from General Electric's Research. Annarita, are you there?
Thank you. Yes, I'm here.
Okay.
Can you hear
you
me?
may
Yes.
start to share your screen. Today, Annarita is going to talk about quantum annealing applied to an industrial logistic problem.
Okay. Can you see my screen?
Yes, we do.
Great. Let me put it in slideshow. Thank you very much, Enrico, and the organizer of this conference. It's really interesting to hear what everybody is doing. Very exciting, and giving me the opportunity to present our work at GE Research. Let me go to just one slide introducing who we are, why we are interested in quantum computing. So we started 2 years ago, and the first decision was we are not interested, at least now, in building a quantum computer. We are interested in applications. So GE Research is the biggest research center for General Electric. And we are upstate New York. We are a big center, like 2,000 people. We are organized by capability. So imagine the artificial intelligence group is like a department in a university. So there are many people for each of the different capabilities. And the projects are divided into vertical when they go deep in one technology. For example, casting is one of them, or horizontal, like, for example, artificial intelligence, that they go across the many different businesses. Quantum computing is part of what we call exponential, which are those technologies that maybe will not bring value tomorrow, but we see a big future for those. So these are a little more far in the future, and quantum computing is one of them. As I said, we started working 2 years ago on this project, and after understanding what quantum computing was, we wanted to develop an application that was resonant to our businesses. So we focus on asset sustainment problem, which I will go into details. And we focus on the aviation business. So imagine we sell engines. We sell a lot of engines, not now, but usually. So 36,000 engines, let's say, usually are GE engines, and there are thousands of parts in that particular engine. So at every single moment, there is something like 36 million pieces that can go wrong. And a big revenue for our company is the service agreement, which means when something has to be maintained, it goes back to the service shop, and there are machines, there are people that work on this particular piece, and then the engine goes back to fly. So this is easy to say, but it's a big process. There are more than 1,000 of this service shop, some small, some big. And the biggest one, they can have 1,000, 6,000, 7,000 machines or people working. So how to optimize this process is not obvious. So this was the application that we wanted to develop. And we built a demo. So if you came to our lab, we would invite you to our lab, and we have a flat screen table where people can actually play with the demo, and that's what I would like to present right now. So let me stop sharing this, and I want to show you the demo. Let me share screen. Okay. Okay, I hope you can see.
Yes, we do.
Oh, great. So why did we do this? Because we wanted to get closer to the people that at the end have to use it. So if we show slides, yes, they can get it, but it's more powerful if they see that it works. And what you'll see here is that actually running a quantum computer for real. So as I mentioned, we see. Okay, we focus on the aviation business, but each of our businesses, they are building big pieces. GE Power is building, for example, generators, so compressor. GE Healthcare is building a scanning machine, and they all need to be assessed. So it's a problem that goes across all of our businesses. And this is an example of one of the service shop, of the aviation service shop that I was mentioning. So there are so many engines, as you can see. There are people around that you don't see here, but there are people and there are machines. And if a machine is busy with one engine, it cannot work on the other one. So how to give priority and even how to place the engine in the right spot, that's a challenge. What they do now they work more on domain knowledge. So the people that work there are very knowledgeable to know the different priorities. They have tools, of course, but it's not possible to optimize the network globally. So there are divided in sub-networks and things work, but even if we push the performance of 1%, it would be a big improvement for the company and for the customers also. So let's go a little deeper in the formulation. So you see an engine that needs to be repaired, and there can be different ways to do it. We can, for example, buy the part from a supplier, the part that needs replaced, or an operator can actually work on the part and we can buy another part, maybe cost less and come faster, or we can 3D print the part. So at each moment you have time constraint, how fast you want this part, and you want and you have cost constraints, how much are you willing to spend? So you can decide. One part is easy to decide. If we go to two parts, you see that this supplier or this manufacturing company, they have to fulfill two needs. So it's still easy, but imagine there are three of them. Yes, we can still do it and we can still find the optimal. So let's say this is the optimal. So our problem is much bigger. So what we built is we gave the possibility to actually work on building the problem that people want to solve. And there are some are smaller, some are bigger. Our what we call hard problem as 42 logical qubits, which actually correspond to the different paths. Each qubit correspond to from each of the repair, which is the path of solutions, of machines, of people that get me to the solution. So these are the logical qubit. So here there are 78 resources and 12 repair to repair. So we build a problem, we formulate the problem. In the formulation, we focus on an annealer. So it is a D-wave machine. So we started with the machine two generations ago, let's say. So we build the cost and the constraints, and this was the hardest part. The cost correspond to congestion. So, for example, this is this model, the congestion in this particular machine. So there are three paths that goes through that, And you can see that there are 3 qubits. These are qubits. They seem complicated, but these are just qubits. And the more they are activated, the more they are 1, the higher is the cost. So we want a low cost. But what is the point here is that you don't want all to be 0, because you want also some constraints to be met. And the constraint to be met means that for each of the repair, you have to choose one path, because if you don't do the repair. So this is one constraint. The other one is that you actually want only one path per repair, not 2 of them. And that's what models the constraints. Then we did the calculation, we put them together. We did some experiment to evaluate the optimal K. And after building the interaction matrix between the qubits, we sent it to the quantum computer. So we can run the quantum computer at this point. And as I mentioned, if you come, we give you this authentication request with your hands, which of course is fake, but just for fun. So now we can run a quantum computer. And as I mentioned at the beginning, in this very moment, we actually are running a D-Wave machine. So we sent the information from upstate New York, where we are, to Barnaby, and we got the results back in 800 milliseconds. At this point, we can visualize the results. And what we get is a ranked list of solutions. So our energy here is 74. That's the minimum energy. Just looking at the graph, if you pick the minimum compared to, for example, the worst one, which is almost 2000, it's a lot different. For example, in this one, there are some that are done twice and some that are not done at all. And even if you pick the one that meet the constraints, so we had some in different color, we chose the one that meet the constraints until 212, the constraints are met. To 376, the constraints are not met. And you can see here that there is one, actually, the orange one, which it doesn't get to be repaired. So that's not what we want. And then we started collecting some data on the machines, which was very useful for us to compare the different machines. So we did 5,000 sample, and 19% were constrained. The minimum energy was 74, the maximum that meet the constraint 2012. And then we have this ratio between the logical qubit and the working qubit, which in this case is around 11, which means for each logical qubit, we need 11 working qubit. And that limited a lot the size, the scale of the problem that we can solve. So just to make it even more real, we have on the left side the real problem. On the center, the white is the logical connection between the 42 qubits. And on the right side, we have actually how the qubits are connected inside the machine, how the logical qubits are connected. So we can see that the white connection are the good ones, and the blue connection are the one that the embedding adds to make it possible. For example, if we see this one has many more connections that the connection between qubits allows. So these logical qubits is represented by all these hardware qubits. And we saw before that the average was 11, so was not great. So what we did, the demo ends here, so let me stop sharing this and I'll go back to the slides. Stop share. Okay, share screen. Let me go back to the slides. Okay, so what we did, how can we get to our real problem? So we started with a very simple problem, 3 repairs, then we go to 10, 30, and that's doable. How can we get to the 15,000 repairs and 6,000 resources? This is the scale of a possible GE problem. We were not able to do that until new hybrid algorithm became available, until new D-Wave machines became available. So we started comparing. So this is a comparison between the performance of the 2000 Q2 and the 2000 Q5. The 5 has a better material. So in this case, we did not see that there was a big improvement in terms of energy. So if you compare the energy level, yes, maybe the 2005 is better, but you really cannot tell. So we thought that the reason was because of the chain breaks. In this case, the topology is the same. So there is always the problem of the chains are too long and they can break. So after this, we compared, and we did this actually before the new advantage became available. We compared the length of the chain, and the chain is what I showed before for each logical qubits. How many hardware qubits can be chained together to represent the logical qubits. And we saw that for the Pegasus, for the new topology of on the advantage machine, the number of qubits in the chains is much less. So we were very hopeful, and we were looking forward to try the same algorithm in the new machine. This is the comparison between the 2000 Q5, 6 and the advantage. So let's start with the minimum energy, which is the bottom left. You see that the minimum energy is not, there is, for what we try, there is not a huge advantage. And we are trying to investigate why that's the case. But we saw a big advantage in the percentile of constraint solution that goes from 20, 22 to almost 40. So that means that the new topology where the qubits are connected, in many more qubits are connected with each other, we have better percentile constraint solution, and this allows for a better working to logical qubit ratio. And you see here that that is much better. Yeah. So one direction that we are taking, since we saw this big improvement on the new machine, is can we go backward actually? So starting from the topology of the quantum computer, can we adjust our logistic problem to fit in that topology without building chains? So we did for the 2000 Q, and we found that the performance was almost almost 100%. Yeah, there were many. You see here, the number of constraint sample was close to the 5,000. So we have many directions. One is to get closer to our businesses. So even if it was possible today to solve this problem, how can we get all the data together to actually put it into the machines? That's one direction that we are following. The other direction is to go deeper into understand the new machine, the new algorithm, and how can we push the boundary even more. But we are very excited about being able to see that in these couple of years, there has been a tremendous improvement in the hardware. Yeah. And then the other direction is to try the same on other quantum computing machines, on other platforms. Yeah. So Enrico, this is what I have so far. If there are questions.
So first of all, thank you so much. And I can see questions in the chat.
Stop share so I can see.
Yeah, because you are too far ahead. I do have one for you, which is, yeah, I understand that you're trying to figure out how to map directly the problems into the graph. Okay, is that correct?
Yes.
Okay. Yes. So my question is, have you ever thought that you maybe can use something like machine learning and deep learning to do that? Is that your strategy?
We also have, yeah, we also have worked with our machine learning people, and one of the direction is also using some machine learning technique to optimize this task in particular. So yes, yeah.
Yeah, yeah. And the second curiosity I have is, I maybe missed the point. What is the reasonable size of problems you would like to solve with respect to the maximum allowed problem you can solve with the best machine you have? Is there a gap, or you can already solve some kind of reasonable problem?
We can already solve that. We were not able to solve it ourselves, but working with the wave and with the algorithm, with the hybrid algorithm that they have, which is not available yet.
So that was not a toy problem, that was a real problem.
It was a real problem. It was a real size, not the real problem. So
okay.
the data because that's another problem, is to get the data needed to do this. That's another whole problem. Yes.
Yeah. It's amazing to see how in practice the quantum technology is working. Yeah, it's really amazing.
Yes, and we were even very pleased when the service shop people came and saw the demo. They were like, this is really what we need, and we were pushing. Oh yes, we can run it like every 10 minutes, and if they had it and it ran one, they would be happy. Yeah.
Yeah. So thank you again for your fantastic talk. And
thank you, Enrico.
Thank you for joining the conference from the United States. And now let's